Electromagnetic control relays. PLCs were designed to replace relays that performed logical operations, things that made decisions about processes. So let's study the relays themselves as an entry point to understanding what a PLC does, and relays themselves are still useful. Now, control relays are not as common anymore as they used to be, but there are other types of power switching relays that are more common. So understanding what a relay is, how it works, and what it's supposed to do will help in understanding PLCs. Now, there are often output modules with PLCs that have relay outputs, so they're not just completely replaced by PLCs. So basically a relay is an electromagnetic switch. It's something where you can apply power to a coil. That coil generates a magnetic field and mechanically moves an arm that changes the status of a switch. So in our diagram there, our electrical diagram, you'll notice that there are two separate circuits. One circuit is driving the coil, and you might say, well, is that the switch that gets changed? Actually, it's not. We have to close a switch. We have to somehow decide to apply power to the coil, and then that coil magnetically pulls in the contacts. You see the red coil closes the contacts on the blue switch up above so that current can flow through the load. Now, why on earth would we need this? I mean, it seems crazy, right? Why not just put the switch that we had to close over at the contacts? Well, the reason for it, there's a couple of different reasons. One reason is that, number one, that switch may be something that a human being would have to throw, and we really don't want very high voltage going through a switch that a human being's hand will be near because of the possibility of electrocution and short circuits. So the relay can help to separate or insulate two circuits from one another because the magnetic link is the only link between the two. So isolation is one, even today, common application of relays. But another reason is that that switch that we show in the lower circuit may or may not actually be thrown by a person flipping a switch like you would a light switch. This may be the PLC making that change and powering up the output coil on the relay. So in its essence, though, a relay is just a magnetic coil or electromagnetic coil that when you turn on changes the status of a switch. Now, it doesn't have to change a switch from off to on. It can change it from on to off, and it doesn't have to just be one single switch. If you notice in the image, there are actually three switches, all of which change state when the electromagnet comes on. So how does that operate? How does the relay do this? Well, if you look at the relay from the side, you can see the coil, which is the sort of aqua-colored item. When you apply power to that coil, what happens is there's a movable contact on the end of an armature. Now, a spring, when the coil's de-energized, holds the contact in contact with one set of fixed contacts, and you can see that the fixed contacts are pink. But when the relay is energized, when the coil is energized, what happens is the relay pulls the armature down so that the armature movable contact makes contact with the lower fixed contact. Since the relay in its default configuration, when it's de-energized, makes contact with the upper fixed contact, that is called the normally closed set of contacts, whereas the lower contact is called the normally open. And normal just means in its normal or usual configuration when the coil is not energized. So even though in the energized state the armature moves down such that the movable contact connects to the lower fixed contact, that lower contact is still considered the normally open contact. And most relays are set up like this, where you have a normally open and normally closed set of contacts for every switch. And of course, when you turn on the relay, it just changes the state from connection on one side to electrical connection on the other. So the terminology normally open is often abbreviated NO, and normally closed is abbreviated NC. We typically give them symbols, as you see on the left upper figure, where there's two lines, two horizontal lines indicating the wires leading up to them, and then a couple of vertical bars. These are not capacitors or anything, if you're familiar with that from electronics. What this indicates is the contacts that could touch each other, and if you put a line through it, it's a normally closed set of contacts, something that by default is touching, and then without that line they are normally open contacts. And here's a slightly different configuration of a relay. It's set up sort of as a schematic, where you see the coil on the right and then the blue armature that is normally just off to the left, probably pulled that way by a spring, such that the left-hand set of contacts is normally connected to the movable contacts. Now the movable contacts would actually be connected to each other, and that would be one of the wires coming out of the relay. But when the coil is energized, then the armature is pulled to the right, as you see in the lower right hand figure, and the normally open set of contacts close so that the movable contacts touch the stationary contact on the right. But the stationary contact on the right is still the normally open set of contacts, and the one on the left is the normally closed set of contacts. Here are some specimens of relays. These are things that I have in my office, for example, or in the lab. The relays vary a lot in size. You can get very, very small relays or very, very large relays. The one on the left was a relay made by a company called SafeTran. They make items for trains, especially intersections and things. This relay sitting in my office, it's literally about 1 foot tall and about 3 inches wide, or deep in this picture, and probably 8-10 inches wide, something like that, in the view we see. What's interesting about this is that it's such a huge relay. I haven't seen a relay bigger than this, although I know they do exist. But you notice there are two coils on the left-hand side, both of which pull down on that bar that kind of goes, it's almost horizontal in this view, and then it bends around and down, and you notice that there's a spring on the lower section of that bar. But when the coils are activated, it pulls down on that bar, which rotates the whole thing, pushing against the spring. And then there's actually, I think, 6, or let's see how many other ones, yeah, 6 different set of contacts in this one. This is not actually a photo of the one I have. The one I have, I think, has 12 switches in it, but it doesn't matter. The point is that there are a whole bunch of switches in this one relay, such that when the coils pull in, it changes the status of a bunch of different switches, not just one. And this is very common, even with the little so-called ice cube relay on the upper right figure. You'll notice that there are 4 switches associated with it. And the way this works, if you look at it, you'll notice that you can kind of trace everything, right? There's closest to us a row of 4 terminals, and those 4 terminals, it looks like, are making contact right now. There's 4 switches that can rotate, but the 4 terminals closest to us, to the left, are making contact with the movable switch contacts. Those movable switch contacts, you can see the white wires that go to, let's see, it's 1, 2, 3rd row back of terminals. And so that's the movable contacts, and then the second row of 4 contacts or 4 terminals would be the normally open set of the switches. So there's 4 of them going across the face of the relay, 4 switches, and then you'll notice there is a 4th row. Well, that 4th row would consist of only 2 different terminals, which are the coils, or the relay coil. And apparently this one runs on 24 volt DC. You can see that printed on the coil inside there. If you notice, there's even a schematic on the top indicating how all of this works. The Allen Bradley example in the lower right hand corner is how these ice cube relays are usually configured. They're made so that they plug into a terminal block, or a socket basically, so that it's easy to replace the relay. If something goes wrong with the relay, you just pull it out and you put another one in, and away you go. You don't have to rewire anything, because all of the terminals are brought out on the terminal block so that you can hook up your wiring via screws permanently or semi-permanently, and when the relay goes bad, just pull it out and put another one in. It makes it very easy. Now, interesting side note, computers once used relays for all of their calculations, and so they were very slow, and the term getting a bug in your program came from the time when relays were operated. And if you think about it, if a bug, an insect, got inside of the relay switch contacts and it prevented the switch from changing state, that could completely mess up a program. And so that's where the term kind of comes from. But obviously we don't use relays for computers today, although there are hobbyists that build relay computers still. Now the symbol for a relay has two parts. There's the coil, and then there's the contacts associated with it. Now these can often be quite a distance from each other in the schematic or the ladder layout, whatever you happen to have. And so they're typically marked with a symbol to indicate the relationship. For example, M is printed on the coil, and then the M contacts are associated with the M coil. In this case, this would typically be used for, say, a motor starter, and we'll talk a little bit more about those later. Control relays, on the other hand, might use CR. So there's a CR coil and a CR set of apparently normally closed contacts associated with that particular coil. And whenever the coil is energized, then the status of that switch or those contacts changes. So, you know, when the coil on our control relay is not activated, then power could flow through that CR switch, but when power is applied to the coil, that would break the electrical contact with the CR switch. And like we've seen, there can be multiple switches all associated with one particular coil. Here's an example where a control relay is controlling two different pilot lights. There's a green pilot light and a red pilot light indicated by R and G. These are common symbols where you notice the bars coming away from them on the R and the G. That indicates that it's a lamp. And so when a switch is closed that is not part of the relay, what it does is it energizes the control relay coil CR. Now, what are we looking at here? Well, this is our first introduction to a ladder diagram. You notice you've got L1 and L2. That indicates the power rails. Whether this is, 120 volt AC, it could be 24 volt DC, it doesn't matter. The point is there's an electric potential difference between L1 and L2. Typically, L1 and L2 are reserved for AC current, but that doesn't matter right now. The point is that power wants to get from one side to the other, and if you put devices in between that can carry that power, power will flow when it has the opportunity. So if we close the switch S on the first rung there, then the control relay would be activated. It would have power across its coil, and it would turn on, changing the status of both CR switches. Notice there's a normally open and normally closed switch. So in the case where the switch S is not closed, then the relay coil is not active. And so CR on the second rung does not conduct power because it is a normally open set of contacts. But the normally closed set of contacts from the relay on rung 3 are passing power, so the green light is on. But when we close switch S, as in the right-hand side diagram, then the control relay coil comes on, and then it's not really appropriate to change the symbols the way that it's been done here, but for the sake of you understanding, now there's a bar through CR on the second rung, and the red lamp is on. The CR switches would not change symbol this way. It would be understood that when CR is active, the normally open set of contacts would transfer power to the red lamp, and the red lamp would come on. So, slight thing I don't like about this, I just realized I need to make a change in these slides. But you can understand that the second rung transmits power, whereas the third one doesn't, because the normally closed set of contacts is now open since the relay coil is energized. Here's an equivalent PLC simulation of that same control relay. I wrote this in the Click programming software that we are going to use. And so switch S is one of the inputs to the PLC, which activates an internal relay, C1. You notice the setup. This looks a lot like that diagram we had a moment ago with a rung on the left and an understood rung on the right, though it's not shown. But the switch S would activate C1, turning on that coil, that output coil. That switch, or that coil, would have switches associated with it. Now in a PLC it's just memory, and you can reference it as many times as you want, so it's like you have a relay that has as many switches associated with it as you wish. But anyway, on the second rung, when that coil comes on, well then the internal relay C1 will pass power to the red lamp. But when C1 is not on, then the inverse of that on rung 3 means that power would be passed to the green pilot light lamp or pilot lamp. So this is just an equivalent PLC program to the circuit we saw a moment ago.